Okay, up to this point in this chapter, very quickly, what we did in this chapter was we started to look at the deformation. In the chapter 1, we look at how the stress in the member would be. In this chapter, we start to look at in the deformation, how it happened, and then after that, we went and says, okay, one application for that deformation was if there is a statically indeterminate problem. So what we were talking about was that if you have a problem that the equilibrium equation by itself is not enough to find all the unknown, we have to go and look at the deformation and somehow find the equation from the deformation to add it to what we have so far. Solve it. Add it to the equilibrium equation and solve it. So up to here, what we have it that says, okay, look at it, this is the object, we put the force, it's gonna deform. How we can deform an object or member without force? Without force.
I'll say, does heat count as a force?
So you can change you can deform the object with the heat or cold.
Okay.
So you can basically change the temperature. So this is one part of the problem that we're going to look into it today. Not very deep, but just have some sense of that. Up to here, all we have looked at it was the force that caused the deformation. Now we are going to have the deformation without any force. So if I heat any object or cool any object, its length is gonna change, and it's gonna become longer or it's gonna be shorter. It can happen both ways. And if the object is not, assuming the object is just sitting there, is nothing restrain it, so it's gonna change. So if it's originally is like this, and then I'm gonna somehow make it put some heat into that, it will gonna stretch to this. So I go ahead and say, hey, this is my heat source. I heat that, so it's gonna stretch. So the original length that I have is gonna be, that's gonna be the L, the original length. And then I have this change in the length that, remember that changing the length can be both ways. It can be the change can be increasing or decreasing, so it can stretch or it can compress. That delta T will be calculated from this equation. Is alpha delta T
Two different, I know that they're both delta, but one is measuring what's the differences in the deltas?
This is the deformation or changing the length. The delta T is change in temperature.
Okay, so they're both the change in something, they're just changes in different things?
Yes.
Okay.
Usually when we use the delta, we want to use it for usually we use it as a change. So for example, say delta X is means changing the X. In the strength of material, specifically a small delta reserved for the change in the length. So instead of writing delta L, they just write a small delta. So the alpha is coefficient of thermal expansion. So it is for of thermal expansion, and it is either in 1/centigrade or 1/Fahrenheit. So depending on what's the delta T, whatever is the delta T, so it's gonna give us in that sense. And the delta T is the change in temperature. And the delta T and L are here, so it's the length and it's the change in the length. So that is length or initial length, you can see. And that's the change in the length. So a strain, what was the strain? Remember the formula for the strain?
P-L-E-A.
That's the deformation, the strain, the epsilon. Force over area. That's sigma, the stress. The epsilon, the strain. The epsilon.
Sigma over E is equal to epsilon, or delta over.
Heard that? The strain is the change in the length divided by its original length. Remember? So now, if I have that, the epsilon T would be, look at here, if I divide that by L, it's gonna be alpha delta T. Correct? So the epsilon T is gonna be alpha delta T. And it's gonna be the thermal strain. Is it strain due to change in the temperature? So I'm gonna just show you two cases. Any question up to here? So, if I have a case equal like that I have assumed, I have a a member that's not restrained in any way has changed the temperature, either getting hotter or colder. So in this case, how much is this sigma? The sigma due temperature.
Just be zero.
Zero?
Yeah.
There's no force in there. If there's no force, the sigma is force divided by area. So no force, so it's gonna be zero. So there is no stress in that object, but the strain, what about the strain? It is not zero. So this is probably one of the cases that we have the strain, we have the deformation, but we don't have the stress. But it's a very, for example, in this case, like if you put a piece of railroad that's not restrained in any way. But most cases is not like that. So in most cases, what we have is that, for example, something like that, that the object is kind of restrained. And if I go there and I heat that, or freeze it, in this case, how much is the sigma t is not zero anymore because it wants to expand, so it starts to push to the support, so the support starts to push back, so there's going to be force in the member. What about the epsilon?
It's not zero either.
It's going to be? Epsilon is going to be 1?
The change in length, well, it doesn't change length, so the change in length would be 0 over L, so it would be 0.
Yeah.
Okay.
Because look at this formula, the delta would be 0. If the delta is 0, it can't change the L. So it's going to be 0. So this is a little bit different from when we had the force. When we had the force, we had the force and deformation usually all together, not all the time. But here, you can have both of them, or you can have one of them. If the support was in a way that it lets it to move a little bit, but not completely, then you had both of them. For example, assume this was come to very close to the support, but not actually hitting the support. Then it will expand until it hit the next support, and then you had both strain and stress. Any questions? So let's look at one example and then we just move on from this.
Right now, we don't have to worry about like the width of the heat source or like the duration of the heat source.
No, right now we just look at the changes as it becomes. This temperature, from temperature 1 it goes to temperature 2. So what's the change in the temperature? As I said, we are going to look at it in the very simplest way.
Okay.
So have an object that point with the something look like this. And the support here, support here. Say point A, point C, point B. That area is 0.6 inch, square inch. This area is 1.2 square inch. And then distance is 1.2 inches. So so I want to find the first thing, want to find if we call that things and again give you temperature. If you want to know the support reaction, the stress in each element, and the strain in each element. So you want to know the support reaction, how much stress and strain I have in the AC, how much stress and strain I have in the BC. So look at it. That's again, if you will have it, it is a indeterminate problem, correct? There's no way, from the statics you basically get nothing. Okay? So, how do we solve this from the indeterminate case? I'm calling it first of all. I'll give you the exact, I'll give you exactly how much we're going to call it. So make it cool. So what happened?
Shrink.
It wants to shrink, but it can't because this bond.
It's gonna be intention.
Yeah. So how do I solve this problem? It's the indeterminate case. For indeterminate problem, there were two methods that we could have worked into that. One of them was that I could have said, hey, I will calculate the entire deformation, how much it would deform under that temperature, and since it cannot move, I would say it's 0. That's one way. The other way that was the superposition method was that get rid of one of the support and then let it move, and then that support should bring it back to where it was originally. That's the second method. The book has used the second method here, so I'm going to use the second method as well. So here, if I want to, I can say it's equal to, and if I go ahead and remove the B, what will happen? It will shrink, correct? So if I remove the B and say, okay, this is the under the change of the temperature, it would shrink. And it comes, for example, to that. How much would this distance? It's going to be the delta T, the change of the, or deformation under temperature. Correct? It means that it deformed that one. Now if I go and put the support reaction, the reaction at the B back on the object, that reaction should brings it back to where it was originally. So if I go ahead and put the RB, compression or tension, tension, so pulling it out. So the RB should pull it out so the total deformation would be 0. So, agree with that? So that's how we are going to solve it. Delta T that we have was, I think, T of the information we have. T1 is 75. So T1 is 75 degrees Fahrenheit, and T2 is negative 50 Fahrenheit. And E is 2.9, sorry, 29 times 10, 29 times 10 psi, 10 to the 9 psi, and alpha is 6.5 times 10 to negative 6 per Fahrenheit. So these are what we know. So what would be the two steps that I have to use if I'm using this method? So first I have to find the deformation due to temperature. The first step. So I'll find the delta T. Or delta from delta T. So how much is the delta T? T2 minus T1. So delta T is minus 50 minus 75 would be
minus 125.
minus 125 Fahrenheit. So that's the delta T. So then use this equation to find the change, how much change that's gonna go. So the delta T is gonna be alpha delta T L. So it's gonna be alpha is 6.5 times 10 to negative 7. Negative 6. And times 120, negative 120. Negative 125. And the length is 24. So alpha delta T.
Isn't it 2.4?
Oh yeah. That's one. No, it says it's 24. Those are 12. 12 is 12. Sorry. Thank you. Yeah, 12. So delta T, the deformation from that would be negative 19.50 times 10 to negative 3 inches. If I have the number correct, it should comes out like that. That means that if there is no B there, and then that can freely shrink, it will shrink, and this is a negative, about 20, no, about 20 times to negative 3 inches. What's next?
No, we have to add the support back and basically stretch it back out.
So now, that's correct. So now I have to go and see what would be the deformation from the RB. So okay, go ahead and say, okay. Yeah. Delta from RB. So if I have the RB, what would be the deformation?
Plus 19.5.
I not just said eventually what it would be, but I don't have the RB. That's the problem. So if I want to calculate the deformation from the RB, what was the equation, the delta from RB? What was the equation? Sigma PL over AE. Remember that? So I need to know the P, if you remember, the P was the internal force, the internal axial force. So I have here, how many terms I'm gonna have? I'm gonna have two because the area changes. But I have one from AC and one from AC. So basically, I need one section here, I need one section here for the P to work with that. In this case, so it's relatively easy. So here, the P for the AB, how much is that? So RB. So how about your P from the BC? It's going to be also the RB. If I cut it and look at the right side, look vortex, right? So it's a normal force. The normal force is there. So the delta from the RB is the delta in the AC plus the delta in the BC. So delta from the RB is gonna be the PI, the PAB, LAB, AAB, E plus PBC plus LBC and ABC. So delta from RB would be RB times 12 divided by area of the AB is 0.6 times E, which is 29 times 10 to the 9 plus RB, that's times 12 divided by 1.2 times 29 times 10 to 9. So delta from the RB would be, if I have it right, it's gonna be equal to 1.0345 times 10 to negative 6 RB.
For the E, you have 29 times 10 to the 9. Where's that number from again?
It's given, it's the,
Oh, yeah.
I think it's for the steel. Yeah, 29 times the 6 is for the steel. Yeah, modulus for the steel. So then the next is the deformation. So how much would be the deformation, the entire deformation?
The entire deformation is 0.
Zero. So the entire deformation is 0. Therefore, the delta from T plus the delta from RB should become 0. Therefore, negative 19.5 times 10 to negative 3 should plus that number 1.0345 times 10 to negative 6 RB should be 0. Therefore, RB would be how much? 18.85. Times 10 to 3. So any question up to here? So up to this point, we find the reaction of the support, and if this is the RB, so the RA is going to be the same, equal in the other direction. Now we want to find out the stress in each part and the strain in each part. So, next part, the stress. The formula for the stress was force divided by area. So sigma for the AB would be the internal force in the AB divided by area of the AB. So the internal force in the AB, how much would be? You know that is gonna be equal to RB. You already have it, so RB is 1885 times 10 to the third divided by area of the AB, which is going to be 0.6. So it will give us two times 10 to 3 pound. The sigma for the BC, the same thing, is the P in the BC divided by area of the BC. The force is the same. The area is double, it's 1.2, correct? So it's gonna be 15.71 times 10 to the third pound per inch. Now the stresses. So now the strain. So first things, delta AB is 0, correct?
Yeah.
What about the delta AC and delta BC? That's very important. Because if I look at that equation, the strain was delta divided by length, correct? Delta divided by length. The total change in the length is 0. So 0 divided by length, so the strain should be 0. Is the strain 0? So why is not 0?
Because we had moved it earlier.
No, here.
Oh,
Look at the original shape. In the original shape, the total change in the length is 0. So, can I say because of that, then the epsilon, which is delta over L, is 0? Can I or cannot? If I can, why? If I cannot, why?
Can't because the strain is also equal to the alpha times the change in temperature.
I know, but what about that formula?
It's not right.
Which part of that is not right?
I'm pretty sure because AC either tracks more or less than the other one. So if you split them up and add them together, it'll equal 0.
So you're right. So that doesn't mean that, and that is wrong. The reason is that although the total change is 0, the change of AC and BC is not 0. Most likely the BC, I mean in this case, because so it goes back and it just stretches the other part. So the AB is most likely stretched and the BC compressed. So although the both part, the entire thing doesn't move, but it doesn't mean the internal element doesn't move. So in this case, the internal element moves. They just cancel each other. So there's a strain there. So it's a very important thing that I want to say, that the delta AB and delta BC is not 0. That's very important. So although the entire shape doesn't move, doesn't deform, internal part can deform. So now we have to go ahead and see the deformation. So if I want to find the deformation in the AC, what caused the deformation in the AC?
If we treat them like two separate pieces, we could look at the force from BC on AB, and then look at what it'll basically just be the force acting on the two sides of it.
That's almost correct. So up to this point, what we learned, what caused the deformation? There are two things caused the deformation up to this point.
Temperature and force.
Temperature and force. So that change, the change in the deformation in the AC should come from both of them, because both of them are present. So partial of that comes from the temperature, which wants to shrink it. And then you have the internal force from the support that wants to pull it and stretch it. And then based on these two, if you put these two together, it gives you the total deformation. So if I'm writing for the AC first, so delta for the AC, sorry, these are AC. AC. So delta for the AC is the delta in the AC from the temperature plus the delta in the AC from the internal force, or basically P in the AC. P in the AC. Okay. So anywhere I have the A is going to be AC. So the change caused by the temperature and the change caused by the internal force in that, correct? So how much are gonna be, so therefore, I can say the epsilon, the AC is going to be epsilon in the AC as 10 plus the epsilon in the AC as a PAC. I can divide the entire thing by L. Now, how much the epsilon is from the temperature? Epsilon from the temperature was alpha delta T, correct? So it's going to be the alpha delta T. So it's going to be equal to, which is the alpha, 6.5 times 10 to negative 6. Times the delta T was negative 125. So if it is correct, it should come out as minus equal to negative 6. The unit doesn't have a unit, or length by length. Sometimes you just leave it like that, or you can say, for example, inch per inch. But just leave it without a unit if you want. Now, how I'm going to calculate this? Because if I want to calculate this, I need to have that. So I can say that sigma is the E epsilon. So I can say the sigma for the AC is the E epsilon for the AC. And that's as a result of the force. So there I can say epsilon AC as a result of the PC is gonna be sigma. Sigma in the AC. Sigma in the AC divided by E. Sigma in the AC is 3142 times 10 to the 3 from here. And the E from here, 29 times 10 to the 9. So it's gonna be 83.4 times 10 to negative 6. So the epsilon in the AC is, again, this equation, epsilon in the AC from the temperature plus epsilon in the AC from the internal force, which is gonna be negative 112 times 112.5 0.5 times 10 to negative 6 plus 1083.4 times 10 to negative 6, which would be 271 times 10 to negative 6. So AC is stretch or compress?
Stretch.
So AC is stretch and then the BC compressed. How much the BC compressed? Negative that, exactly that amount, because if it is stretch, assume 1 inch, the other one should compress 1 inch. So I'm not gonna do the calculation for the rest, but you can do the same calculation for the BC. I'm just gonna write it here. If I go ahead and write it, so I would have the same thing for delta for the BC or the L. I'm gonna write directly the epsilon. The epsilon for the BC would be epsilon in the BC as a result of temperature plus the epsilon in the BC as a result of internal force. Which if you do the calculation, you will come up with the negative of that 271 times 10 to the negative 6. That's exactly the same, just same formula. So, any question about the temperature? So, up to this point, we assume that when we put the force on any object, if we compress it or stretch it, all happens is in the direction of the force. But you probably see that if you just has a stretch band and you stretch it, so it's stretched from that in that length. What happened to the width?
It's skinnier.
It becomes skinnier, so it decreases, and so if you pull it, it's eventually snap. But so you know that if I get pulling it apart, there's gonna be a change in the other direction. So the width is going to get smaller and smaller and smaller and smaller. This is something that we completely ignored up to this point. So I said, if it's gonna deform, only deform in the direction of the force, and doesn't change in the other direction. The same thing, if you have something and you push it, usually it gets bulkier in the middle. So there's going to be a deformation in the width if I push it. So that's where the Poisson ratio comes to in picture. I said, okay, if we have change and deformation, what would the effect of that deformation in the other direction? So what we had so far was like that. So it was, I have an object, goes there, and then I put a force on that. If I put a force on that, that force causes the deformation like this. And call it the delta. But in reality, it doesn't work like that. So in reality is that if I have the same object, and I'm gonna pull it, it's gonna stretch in the length. So the length would be stretched, but it's gonna compress in the center. So still it's gonna be the delta. And then if I have this as a x and this as a y, in this case, I have a sigma and I have the epsilon, correct? So in the x direction, the sigma x is positive. Sorry, the sigma x is positive. The epsilon in the x direction is also positive. I have the stress in the x direction and I have the deformation in the x direction. What about the y? How much is sigma in the y direction?
Less than 0?
It's negative. Is it?
Press it.
The sigma is the force divided by area. What's the force in the y direction?
Oh, yes, it is positive.
So what's the force in the y direction? Sigma is always force divided by area.
Yeah.
0.
There is no force in the y direction,
Oh,
correct?
correct.
So the sigma, so the stress is gonna be 0 in the y direction. What about the epsilon in the y direction?
It's gonna be negative.
It's gonna be negative, because compressed. So, up to this point, we completely ignore the second part. We only focus on this part, that okay, let's not worry about that part. And in some material, you might, in some cases, you might see the lateral deformation, you can just ignore it. But if you do need to change it, so you have. Then that Poisson ratio, usually it's called with the nu, the Greek word nu, and it is equal to, that's very important, negative. Lateral strain divided by axial strain. In other words, it's equal to negative in this case epsilon y divided by epsilon x. So epsilon for the x is sigma x divided by e. What about the epsilon for the y? And it's equal to epsilon for the z as well. Just remember that. Because I draw it in the 2D, but in the 3D is also shearing in the z direction as well. It's shearing the same way as well in the z direction. It's gonna be based on that equation. Epsilon y is negative nu epsilon x. Correct? So it's gonna be negative nu epsilon x. Or is equal to negative nu sigma x divided by b. can I write the epsilon y equal to sigma y divided by E? And epsilon z is equal sigma z divided by E? These two are wrong. Make sure in this case we cannot use it. If I have the axial force in the x direction, as I said, we don't have any sigma in the y direction, we won't have any sigma in the z direction either. So the only way that you can calculate the epsilon y and epsilon z is that you have first to calculate epsilon x and then multiply it by negative nu to give you the epsilon y or epsilon z. So in this case also I can say, for example, I don't have it, but I can say that sigma z is also 0, but epsilon z is going to be negative. In this case, if I had the z. Two cases here. And if the epsilon is positive, it means that epsilon y is equal to epsilon z would be negative. If epsilon x is negative, it means that epsilon y is equal to epsilon z would be positive. So in other words, if you stretch it in one direction, it should be compressed in other direction. So you cannot stretch it in one direction and get a stretch in other direction as well. They're always going against each other. So, any question about concepts of that? So we have, assume we have a shape like this. It's a broad shape like this. And it is pulled with 12 kilonewton force. And the length is 500 meters. Diameter is 16 millimeters. So again, it's going to be x and y direction. So we have that. It says that if we put that forces on that, what we are gonna get is delta x. So 300 micrometer and delta y of negative 2.4 micrometer. If this is the case, so I put 12 kilonewton on that, it stretch 300 micron and then compress 2.44 micron in the other direction. If it's the case, it says that what's the E and what's the nu for that material. So what's the E and what's the nu? So let's start with the E. If I want to find the E, what's the equation for the E? Sigma is the epsilon, correct? That's the equation that I can use it to find the E. So if I want to use that, I have to find the sigma and the epsilon to find the E. How do I do that?
For the epsilon, do deformation over length. And then for
E
or
one
for the strain or the stress, it's just the internal force over there. Right?
Agree? So first of all, which direction?
X.
All you said correct in the x direction. So in x direction, so for x direction, so sigma x would be f divided by area. So it's going to be f divided by area. How much the f is the 12,000 Newton divided by area, which is the pi times 16 times -3 divided by 2 to the power of 2. Which should come out as 59.7 times to the 10 to the 6. So that is how much stress I have in the x direction. How much strain I'm gonna have in the x direction. The strain, what was the strain formula?
Deformation over length.
Deformation over length, delta over L. So how much the deformation in the x direction?
300 micrometers.
length, which is 500 millimeter. Which comes out as 600 times 10 to -6. So now that I have these two, I can write that sigma x is E in the epsilon in the x direction. Therefore, the sigma x is 559.7 times 10 to the 6 equal to the E times 600 times the 10 to the -6. So E would be, if I have everything right, to the calculate that,
I got 9.95 times 10 to the 10.
just the 10 to the 9, great. Let's go. Start. Let's go. Okay. Now how we can find a new? I have the epsilon x for the new, but I don't have, so I need to find the epsilon y, correct? So the formula for the new is negative epsilon y divided by epsilon x, correct? I already have the epsilon x. How much would be epsilon y? So I can use the same formula here, correct? So epsilon y would be the delta y divided by what?
The height.
The height or
Thickness.
Length?
or is circle.
Oh, diameter.
Down. Says negative, so it's gonna be negative, so not negative. So epsilon y, delta y is given as negative 2.4 micron, 2.4 times 10 to negative 9. Negative 6. Divided by, how much was the D? 16 times 10 to the negative 3. So if I have them right, it should come in negative 150 times 10 to negative 6. Is it right? So now that I have the epsilon x and epsilon y, so the new is negative epsilon x over epsilon y. So it's going to be negative 600 times 10 to the negative 6 divided by 100, negative 150 times 6, or the other way around. 6 divided by 600 minus 10 negative 6, so I know what becomes 0.25. I have it. Correct. So usually, it's not this part, the concept of that is important, so you know that if you have the axial force, you are gonna have the lateral deformation. So you don't need the lateral force for that deformation. Any question? Okay then.